Yes, my name is Pablo Fuentes, and I'm from Makepath, and we're here to talk about normalizing data at public scale. We really want to thank Geoawesomeness for having us here. I'm here with my business partner and co-founder, Brendan Collins. We also want to thank Regrid. So Regrid is one of our partners. They've been an invaluable resource for us in our projects. Matt just did an amazing presentation showcasing a lot of the things that Regrid does. And we've used them very effectively in projects. So we're very grateful to them and very grateful for the invitation. We're going to share a few ideas about what it means to normalize data and to clean data. Again, as I mentioned before, I'm the co-founder of Makepath. We are a spatial data science firm based in Austin, Texas. Now, we are a global company. The company was started with my business partner, Brendan Collins, who's also who will be presenting the second half of this presentation. We do spatial data science. We focus a lot on open source. So we're very, very interested in the scientific Python space and the libraries in that space. We focus on geospatial applications and visualization. And we hire a lot from open source communities. So if you're interested in open source in geospatial libraries, Brendan's going to tell you a little bit more about this later. Specifically, we're going to have a few posts that we are hiring for that if you're interested in, we'd love to hear from you. We started Makepath in February of 2020 and as a fully remote company. So before we knew that the world was going to be shut down, we started as a fully remote company. Now we have 15 people and we're growing and we're hiring. So we're very excited to be here. We're very lucky to work with folks all the way from the Fortune 50 to startups to nonprofits. As you can see right there, Regrid is one of our premier partners. But we're very fortunate to solve problems. The common thread here is that all these people have very large amounts of data and very real problems that we can help solve. Just really quickly before we get into data, this is an example of a project that we've done that it mixes private data and public data. So NCX is a leading carbon marketplace. It connects companies and landowners and stakeholders and communities to look at how to offset carbon emissions. And this dashboard showcases how carbon sequestration changes over time. It's a dynamic dashboard, and we build fully functioning interactive products. So we do everything from the design to finding out. We basically build products using this data. And again, for this project, we use a combination of private data and public data. So what is public data, right? So public data is basically available for anybody to use and access. But I want to draw a distinction between what public data is and what open data is, right? So open data is, this is right here, a nerdy machine learning joke where you basically, the teacher telling Robbie to go, go to to clean the data, right? But open data is formatted and is easy to use, it's standardized, and is accessible, right? And so you have an example of, for example, census data, right? Census data can be painful, hard to access, and it comes in unfriendly file formats. And we want to process it and make it easy to use and deliver it in files that match the application to which, the way in which it will be used. So at Makepath, we're actually currently doing this, and we will make some files freely available. And Brendan will talk more about that as well. In Q4, we're coming up we're doing this for people and offering it to the public for free. But again, the bottom line, you're looking at this is that the data has to be clean, and has to be munged, has to be prepared for it to be useful. According to the 2020 annual State of Data Science surveys from Anaconda, 45% of data scientists' time is spent getting data ready for use. So loading that data, cleansing the data, getting in the right format, et cetera. The fun part of data science, so model training, model selection, training and scoring, deploying models is only about 11, 12% each. So about a third, the fun part of data science is only about a third, right? So let's think about it a little bit more. How should we think about public data versus open data? So again, public data is all of the data in the public domain, and then open data is structured and well maintained, right? So how do we go from A to B? How do we get to the subset of data that is actually useful for us, starting with public data? So in order to leverage public data, we got to choose a format. what is our analysis? What is our end goal? You can choose, whatever format suits your analysis, but we have to do things like adjusting values to correct scales, right? So we have to make sure that the data is both useful and is accessible to us, and that we have all the right programs to process it and the right libraries installed. And when we talk about cleaning data specifically, that involves things like making sure that every variable is in a separate column, right? And this, I may be preaching to the choir here, and obviously with an audience of data scientists, these are things you already know, and we're highlighting. This is a lot of what the work that our partners at Regrid do that's so valuable, right? And making sure that every variable is represented in the right data type, right? Number versus text, and that every observation is in the same row, right? So when we look at clean data versus something like this, where immediately you would say like, oh, there's plenty of data here, but really there's a few issues. And we'll go through a few examples here of data that initially looks like it may be complete, but really you need to make sure that is usable, right? So in this dirty data example number 1, right? So the first and second row is every variable doesn't have its own column, right? So you really need to make sure that for this right here, the city column, you see, city and state are in the same, and then you have different formats for zip, right? And our second example, the first and the third row, you have the incorrect data type, right? So you need to make sure that like everything matches up. And then for our third example right here, the first 2 rows should essentially be one row. So every observation, right, doesn't need to have its own row. So if you say this should be an example where we would merge those into a single record, right? Now we think about the 3 different types of data categories as we've gone through. So you have unstructured data, semi-structured data, and then structured data, right? So you start with unstructured data, which is raw, typically unorganized, and I'm sure many of you have dealt with this before. So there's no predefined data models, very difficult to search. It could be things like, you have text, PDF, images, video, data's in different places. It shows the why behind the data, but that's about it. It resides usually in applications and data warehouses and data lakes, and it can be stored in different formats. Now there's a bridge, the semi-structured data, right, that goes between structured and unstructured. And this kind of data is more loosely organized, and you have meta-level structures that contain unstructured data. So HTML, XML, JSON, and it resides usually in relational databases and tag text format and stored in abstracts and figures. And one of the things here is sometimes you encounter, the Pareto efficiency, the 80-20 problem, right, where you have 20% of the effort that gets you 80% of the way there. Depending on the analysis you're doing, that may be okay, but most often, if you want to get to really good, solid analysis, you need to do that very difficult last 80% of the work that gets you the last 20% of the results to get to structured data, right, which is highly organized, easily decipherable. You have predefined data models. It's very easy to search. It's text-based and shows you exactly what is happening. And this it usually resides in relational databases, data warehouses, and is stored in rows and columns. One big thing is that as we think about this kind of data, it's very important to make sure that data is continuously updated, right? And this is something that Regrid does very, very well. Data is not like wine. It does not get better with time. You're more likely to end up with vinegar. So make sure that the data that you're using is constantly updated, especially in the world that we live in now as things change so fast. And normalizing public data is really, really hard, but it's really necessary. And that's the kind of thing that our partners do to help us build visualizations and products that actually tell a story that is true and where you can derive insights for our clients and partners to be successful. Now, it's one thing to talk about normalizing data. It's another thing to talk about normalizing data at scale. So here I'm going to pass it off to my partner, Brendan Collins, who's going to start sharing his screen right here.
So let's talk about scaling data. So Pablo was talking about cleansing data and cleaning up data, but let's talk actually about scaling. So there's two fundamental axes to scaling, and we think of them as vertical scaling and horizontal scaling. And I'm going to talk a little bit about this. So vertical scaling, we're thinking about making our programs faster. So taking an individual algorithm or function and seeing how much data we can push through it at what speed. Horizontal scaling, we think about as being able to take that fast algorithm and scaling it across multi-thread or multi-core or multi-machine. And so these are the two fundamental axes you should be thinking about in terms of scaling your analyses. There is an additional scaling factor that I just wanted to talk about, which is programmer productivity and analyst productivity. We use Python because it's a very simple language to pick up. There's a lot of folks that know it. There's a huge community full of good resources that you can draw from. But it does have some vertical scaling problems. So Python is generally thought of as a slow language, while things like assembly and C are thought of as fast languages. But that's not really always the case. And so in talking a little bit about vertical scaling, and what we're trying to do here is have the programmer productivity of Python with the speed that comes at using a lower level language. So, and vertical scaling on making our algorithms faster, we focus a lot on using NumPy at some level. So NumPy gives us the ability to allocate memory at the C level, but still interact with it within Python. It's a fundamental library for Python data science, and one that many folks will be familiar with. Essentially, NumPy gives us multi-dimensional typed arrays so that we can have a single type for many elements, as opposed to something like a Python list, which is a heterogeneous collection where when you're looping through it, you would need to actually type check every element. So NumPy in the Python world is one of the fundamental libraries for vertical scaling. Wes McKinney and folks within finance came along and created pandas. And pandas allows us to have a data frame, which is analogous to an Excel worksheet with rows and columns, and is structured where each column is a NumPy array. So we get all the benefits of NumPy, which is the speed side, with the niceties of labels, so that we can add labels on top of variables and refer to things via a label instead of an integer index. And that's what you'd get from NumPy. When you say slice a NumPy array, you'd be using integers. So here, pandas is one of those fundamental libraries to help you with data normalization while staying within a productive language, which is Python, and having the speed of C order of magnitude for doing transforms. And just to add on here, another group came along and said, hey, I think we can add a geometry column to a pandas data frame. And that would give us a really nice representation for vector data. So as we think of geospatial vector data like shapefiles and geo-packages, GeoPandas is a really nice library that you can use for doing data normalization, where you're, again, still in Python. All your transforms run quickly because they're using NumPy. But then we also have a geometry column for storing our points, lines, and polygons. So GeoPandas really ties everything together in terms of vertical scaling for vector data, where we have an efficient language with efficient data structures. I also wanted to mention Numba. So for folks that may be familiar with Python but want to extend Python, you can look at using Numba, which is a just-in-time compiler for Python. So this is a vertical scaling solution where you can write efficient algorithms in Python without having to delegate to something like a C extension. And so Numba is a great library. We're using it a lot across a lot of our open source projects. It also allows you to target things like GPUs, which is great. So it's really nice being downstream of Numba. It's easy to pick up, and gives you a subset of Python that you can compile down to LLVM bytecode, which will run much faster. And just talking a little bit, so CuPy also on the vertical scaling solutions. So CuPy is an implementation, a subset of NumPy API, but on top of CUDA-enabled GPUs. So we're thinking about NVIDIA GPUs. And CuPy is really easy to use and is one of those libraries that you could think about. Now, just a word of warning, if you are going to use a GPU, you need to justify that computationally. You need to have a very intensive computation to justify, one, the additional cost of adding the hardware, but also the additional time of moving memory between a CPU and a GPU. But CuPy is a really great library, and if you guys haven't seen it, then I would check it out. Now, on the horizontal scaling side, we're talking about scaling to multiple cores and multiple threads and machines. Dask is what we use for horizontal scaling. So Dask is essentially a graph engine that you're able to create a graph of tasks and then spread that over all the cores in your computer or multiple machines in a cluster scenario. It also implements a Dask data frame. So we have an analogous data structure to the Pandas data frame, but you're interacting, with sequential code, but you can scale it over many machines. So Dask is a library that folks should check out. And now, and this is still an experimental project, but is really good, we have Dask GeoPandas. So as we think about scaling geodata, Dask GeoPandas is a really great solution, and also gives you a nice hook into being able to write out to the Parquet file format. We in performance in general in terms of code has two dimensions, compute and I/O, and Parquet is what we tend to use to optimize for I/O. So when I think of optimizing for input output of data and making sure that we can do fast reads from disk, Parquet fulfills our needs, and those needs fall into the category of four things, which is we look for binary formats that support a variety of different compression techniques that are also partitionable and store data by column. So one thing you can do in terms of scaling is making sure you're storing by column, which means that you can sub-select out data, which means you're reading less data into memory, as opposed to reading by row, which you would see in, say, GeoJSON or a CSV, where you have to actually read each row to keep going. Now, we've talked a lot about vector data and attribute data, but we're also very focused on raster data in the geo world. So we put out a library called Xarray-Spatial, which uses Dask and Numba and can target GPUs specifically for raster functionality. And so just wanted to also mention Xarray-Spatial. If you want to learn more about what we're doing at Makepath, I'd recommend you go over to the Makepath blog, where we're regularly talking about new projects that we're excited about, or new releases in either Bokeh. We're active contributors to the Bokeh library and Datashader and Xarray-Spatial. And we also put together a infographic which explores the history of open source GIS tools. Itself is an open source project, so if you know about any GIS tools, open source GIS tools that we may have missed here, we'd love to get a pull request, and we can post a link to this infographic. As Pablo mentioned at the beginning, we are hiring. We have a bunch of different positions. We're a global company, and we love folks that have a passion for open source. And in any case, we always like connecting. So, please reach out to myself or Pablo, and I'm always happy to jump on a call and talk more about some of these open source tools. So thank you guys so much for attending, and thanks so much to Regrid and Geoawesomeness for having us here.